post this online for people who are absent so they can get their notes. Today we're going to talk about electricity. And there's two types of electricity. Anybody know the two types? Two main types.
Solar and electric.
No, but good guess. AC and DC. I mean, I bet there's other kinds. Like, is static electricity one of those types? I don't know. But AC stands for... I don't think so. So our two types of electricity are alternating current and direct current. Alternating current is the kind of electricity that's in the wall outlet at your house. So here at school also, when you're over at one of the workbenches and there's a power strip or a plug, you can, those plugs that you plug in things, those are alternating current. What's up is the wire has, electricity is electrons moving through a wire. And in alternating current, they go back and forth. So rather than just going from one place to another place, they generate power by going back and forth. And so, like these light bulbs, and probably not these because they're fluorescent tubes, but a standard incandescent light bulb, that it lights up because the electricity is going forwards and backwards 60 times a second. And that movement of the electrons makes the electricity be able to do work. And that's different from direct current, which just goes from one side to the other side. So we're going to go DC, electricity or electrons move in one direction. And these have a plus, a positive side, and negative side. This is all batteries. Solar cells. What else is direct current? The inner circuits of most appliances. So, like your cell phone on the inside, it's running direct current. All right, all our solar systems are using DC power. Solar systems will use DC power. All right, and we've got, let's see, 1, 2, 3, 4 ways to talk about electricity. So the first is volts. You guys have heard of that? Volts? Yeah. You got 12 volt battery, 1.5 volt battery. House current is 110 volts. It's a measure of, boy, that was an ugly F, of force or electrical pressure. Between the plus and minus signs of a circuit. So an example of volts in like the real world is if you have a tennis ball and you drop it from 3 feet and it hits something, it hits the ground with a certain amount of force. If you drop the tennis ball from 6 feet, it hits the ground with a little more force. And so thinking about the force behind the electricity, the pressure in a way. Another example is if you have a water tank with a hose on it, the volts would be a measure of how hard the water's coming out of the hose. You know, you've had a hose that has water coming out hard, or a hose that has water coming out kind of dribbly. That's low voltage and high voltage, or the reverse. Another example is a waterfall. So I'm going to draw a waterfall because I'm a really great artist. Here's a waterfall coming off a cliff. And here's another waterfall. See, here's the river where it goes on. Which one has more voltage, if we were thinking about... yeah, the A. They have the same amount of water. See, I did 4 lines coming down on both of them. Like they're the same width, but the one that has farther to fall has higher voltage. This would be the higher voltage. It's helpful at times to think about these things in different ways. Questions? So that's volts. We were talking about volts. The second way we talk about electricity is amps. And amps, it's the amount of moving electrons. It's also called current. This is an interesting one because have you ever touched like a doorknob and you've gotten shocked? Yeah. It's static electricity. That kind of electricity is sometimes up in like the 10,000 volt range. But the current is very, very low. That's why you don't die when that happens. Like you think 10,000 volts is going to kill somebody, but 10,000 volts is a very, very, very small amount of current. Can hop over the air and shock you when you touch the doorknob. But thank goodness it's not 10,000 volts and 10,000 amps, because that would just cook you. So if we go back to the ball example, current or amps is like having a bigger ball. So instead of dropping a tennis ball from 3 feet, what if we dropped a basketball from 3 feet, or a bowling ball? A bigger object is the example here. Or if we're going back to the waterfall, if we had a lot wider waterfall, that would be, even though they're the same height, here's a little creek of a waterfall on the right and a huge waterfall on the left. This one would be more amps. More amps. Less amps. And so we care about volts and amps because when we're making a solar system, we want it to be able to power a particular device. And you can imagine it takes more energy to power, say, a computer or a television or a toaster than if you were trying to power a cell phone charger. Cell phone chargers, I don't know, just a sec, are like 5 or 10 watts of power. We're going to talk about watts next. And then, a toaster is like 2,000 watts. And so, watts are based on volts and amps. Anyway, Zane.
So is that basically like same current, just bigger impact?
Same current, bigger impact would be more volts. But more, something like a toaster uses more current and more volts, everything more. Okay, so our next measurement, we have two more, watts. Watts is our a rate of energy usage, and watts equals volts times amps. So we have a little math here. This formula, we'll end up using this. So let's say you have a 60-watt light bulb. Hopefully, I don't know if any of you know, but that'd be a common household light bulb that's not LED. We're talking about an incandescent, old style bulb. And let's say our home current is 120 volts. I know I said 110 earlier. Anywhere 110, 120. We're going to say the house current is 120 volts for this problem, and I'm going to say how many amps is that light bulb using. So we have a 60-watt light bulb, and it's running on house current, 120 volts. How many amps? Well, we're just going to use algebra to solve this. We have 60 equals 120 times A. What do I do to solve this equation? Somebody who's big on math.
Wait.
Alex.
So, 60 and 120 there, wouldn't that just be 0.5?
Yeah, but so how'd you get that? You get that by dividing both sides by 120.
Yeah.
But yeah, you're absolutely right. So then the 120 cancels out here, but then 60 divided by 120 there, amps equals 60 divided by 120, or a half, or 0.5, anything along that is fine. So half an amp, that gives you an indication. If you have a regular household light bulb plugged into the outlet, it's using half an amp of power. So it's not so much. And yet, if you touch the wires that did that, you'd get really badly burned. So half an amp is a good amount of juice at 120 volts. It could definitely cook you. So what we're getting at here is just using that watts. I'll just write the generic formula. Watts equals volts times amps again. And let's do another one. We have a solar cell that is it's putting out half a volt, and it's putting out 0.4 amps. And so how many watts is that? Let's just multiply. 0.5 times 0.4. It's got a 2 in it, but 5 times 4 is 20. But then remember, there's 2 decimals up here, so you have to move the decimal point over 2 places. So it'll be 0.2. I'm fine if you use a calculator for stuff like this. I got one more example. We have a 12-volt solar panel. That's a pretty common panel. And it's generating 1.7 amps. And so how many volts is that? Sorry, not how many volts. How many watts? So watts equals volt times amps. So we got 12 volts, 1.7 amps. So it's just 12 times 1.7 equals 20.4. Yeah, you got a calculator on your computer there. 20 watts. All right, we're almost done for today. Thanks for staying engaged here. The last thing we have is watt hours. Watt hours. It's kind of crazy, all the terms and things, but have any of you heard of the term kilowatt hours? That's how power is measured at home when you get a bill from the power company. It says you used 1,000 kilowatt hours this month and you pay 20 cents per kilowatt or something like that. A kilowatt is 1,000 watts used for a whole hour. A kilowatt hour is a kilo stands for 1,000. Yes? A megawatt. Yeah. Yeah, so power plants are measured in megawatts and home usage is in kilowatt hours. Yeah. So a watt hour is pretty simple. It's a watts times hours. I mean, watt hours. So 60 watt bulb that we were just talking about, running on for 5 hours.
No, 30 kilo. Yeah, 30 kilowatt.
Not 30.
300. Oh.
Uses 300 watt hours. You know, another way to think of it, you know, there's 100 watt light bulbs. If you had a 100 watt light bulb and you left it on for 10 hours, that's a kilowatt hour. 100 watt light on for 10 hours equals 1,000 watt hours. Sorry, I need to find my eraser. I said it was a 100 watt light bulb. 1,000 watt light bulb would be pretty insane. Am I back to my thing? Yes, I am. A 100 watt light bulb on for 10 hours is 1,000 watt hours, or we say 1 kilowatt hour.
Wait, what's the? I thought those were kilowatt hours.
Or
Oh, they're watt.
kWh. So we could look up, I don't want to do it right now, but it depends on where you get your energy, how much a kilowatt hour costs. Because you can buy, around here you can buy your power from a company called Sonoma Clean Power, and you pay a little bit extra, and the power is coming from the geysers, which is completely renewable, versus buying power that comes from a nuclear power plant, or and so you know the amount you pay at home depends on where you buy your power. So I want to do one more little calculation, and it's, if you look up here, we've got 17 banks of these fluorescent lights. There's 17 of them in the room. Each one has 4 lights in it, but I've got either 3 or 4 of them are burnt out. 1, 2, 3, 4. 4 light bulbs are burnt out. So I want to calculate how much power we're using here when all these lights are on. So we've got, since we have 17 banks, and each bank has 4 lights, but 4 lights are burnt out, let's just say we have 16 banks of lights that are working right now. Each one has 4 bulbs. So I already heard Jackson say that's 64 bulbs. Each uses 35 watts. All right. I want to know how much power that uses in 1 hour.
Watts times hours.
So this would just be 64 times 35. I need a calculator. Somebody already do it?
2,240.
So 2,240. I'll confirm. Somebody.
I got the
Okay. So that's watts per hour. So that's a kilowatt. 2.2 kilowatts per hour. And if we were going to say, let's say, how much will it use in 1 school day? Let's say I leave the lights on for 7 hours. That's 1 day of school. Boop. So 7 times 2240, 15,680 watt hours. Not watt hours. Or is it watt hours? I think it is. So we're using about 16 kilowatt hours per day, just on the lights. And if we were charged, say, 20 cents a kilowatt hour, the lights in this room would be costing us like $3 a day to run. It's not too bad. I mean, it'd be interesting to calculate what all the computers use and the laser, and all that. But all right, everybody. Good work. That's it for today.